Alright, we ready? Ish. As we're ticking down to the end of the semester. Alright, so as a reminder, 1, you have mastering due tonight. We're going to do a group quiz on Friday and then review in class for the exam on Friday. So I guess as you're doing the practice exam, just let me know if you have questions or specific things you want me to go over. Your exam is on Monday. And then the final exam in here, which is cumulative, is on May 1st at 8 a.m. This is like the second day of exam. So this exams this time are Thursday, Friday, Monday, Tuesday, Wednesday. So if for some reason you are going to have a conflict with that, let me know sooner rather than later, and we can try and sort out an alternative time for you to take it. But it shouldn't be a conflict for anybody who's a senior or shouldn't have that many exams. You know. Alright, in that case, let's finish up chapter 18. So everything up until now, right, we've been assuming standard state. Alright, what concentration am I at if I'm at standard state? Yep. So standard state, which is, alright, that guy. 1 molar, what pressure do I need to be at? 1 atm, what temperature do I need to be at? 298 Kelvin, right? 25 degrees, 98. Alright, so what if I am anywhere but there? Alright, so what if I don't have 1 molar? Or I'm not at 1 atmosphere? Or I'm not at room temperature for some reason? The voltage must change because we are no longer at standard state. So we have done something to the reaction that forces the voltage to be different. In particular, we're going to be looking at concentrations. So we could be doing it at different pressures or different temperatures, but for the most part, we're going to be looking at concentration issues. So in general, you'll see that the voltage increases if the concentration of the reactant increases. Why would those be related? If I make more reactant get started by Le Chatelier's, what must also happen? I put more reactant in. I have to make more product, right? It's going to shift to products, which that is a measure of voltage, right? So as I make more products, I'm going to have more voltage being made. So Le Chatelier says that if the concentration of reactant increases, I must by default see more voltage be made. Alright, now I'll write the opposite statement if you have both. Right, so the voltage must also decrease, the concentration of reactant decreases. Alright, so if I have option 1 and option 2, which option tells me that the reaction is even more spontaneous? What does voltage have to be if it's spontaneous? Positive. So which one makes it even more positive? 1, right? So if voltage increases, if the concentration of reactant increases, that again should make sense, right? I have more reactant, which is going to shift the product. The more products I'm making is more spontaneous towards products, therefore voltage has to increase. All right, kind of bringing all those concepts together. Alright, so if those things are all true, we must have a mathematical equation that puts all those things together. We in fact do have a mathematical equation that puts all of those words together into one compact equation. Alright. Alright, let's go on. I guess I'll start with it. Alright, we had that from chapter 17. What state is this delta G in? Standard state. What's Q tell me? I'm not at equilibrium. So this is a measure of how far away from standard state I am, right? So if this is standard state, but I'm not at equilibrium, this is telling me how far away from equilibrium I'm at. So that's from chapter 17. And then we also had right? Those would also be true. We talked about this one, and that one would also be true, right? Both are at standard state or both are not standard state. What do you think I should do next? I'm going to plug them in, right? So now I have something to substitute G's for E's. Alright, is this E the same as that E? No, right? This is not standard state, that's standard state. But a lot of the other things are the same. The N's will be the same, the F's will be the same. So I can rearrange it. To this. My measure of how far away from standard state I am is dependent on Q, just like we saw up here. But now it also has to take into account the temperature you're at and the number of electrons being transferred. This is so famous it has its own name. This is the Nernst equation. Alright, so let's look at some implications of this equation. Alright, what value of Q do I look at? So, is Q ever equal to 0? No, right? It's a fraction. You can't have a Q equal to 0. So I can have Q greater than 1, right? Because Q is a fraction, so I'm going to compare it to 1. If I have a Q greater than 1, what do I have more of? I have more products or more reactants? Okay. Alright, so I have more products. What would be, let's say Q is 10. Is the natural log of 10 a positive or negative number? If you don't know, pull out your calculator and double check. And we'll do it together. There we go. Positive or negative? Excellent. If the natural log of Q is a positive number, bless you, bless you. What about this fraction? Is this fraction always positive or always negative? It's always positive, right? What's R? Positive. What's T in Kelvin? Positive or negative? F, always positive. Number of moles transfers, electron transfers. Always F, constant, always positive. So I have a positive thing times a positive thing. So I got this negative sign, right? So if Q is greater than 1, then you have more products. This value is positive, so I'm saying E equals E0 minus some whole positive number. You'll find that E is less than standard state E. Right? Because if standard state E was 20, and this is 5, and this whole thing together is like 2-ish, well then the value I get here must be, the final answer is less than what I started with, right? Because I've subtracted off a whole number. That'll be a big deal here in a little bit. What if I have Q less than 1? What do I have more of, products or reactants? Okay. What's the natural log of Q if it's less than 1? Positive, negative? Don't know. We'll double check. Should be the opposite case. Let's get the lighting in here figured out. There we go. ln of 0.5. Negative. Excellent. So that's less than 0. So then, which one's going to be bigger, non-standard state or standard state? Yep. Which should make sense, right? If I have a lot more reactants, which way is the reaction going to go? To products. If it's going towards products, am I going to have more or less voltage? If I have lots of reactants, I'm going to have more voltage. So I would expect the voltage I got is even better than what I could have had. Alright, we'll do some practice problems, that'll make sense. Alright, what if I'm at this point? What does that tell me about the ratio of products and reactants? Equal. What's the natural log of Q if Q equals 1? How are E and E0 then related? Where am I at? I'm at standard state. That's where this one's tricky. So, right, what would Q have to equal to be at equilibrium? Not 0. It equals another letter. K. So, put this in a different color. Right, so if you're at equilibrium, Q equals K. Here I'm at Q equals 1, which may or may not be equal to K. I don't know where I'm at in comparison to K. All I know is if Q equals 1, Q equals 1, you've returned to standard state. You're back at 1 molar, 1 atmosphere, 298. Okay, so similar, but slightly, they tell you slightly different things. Alright, so you will need a calculator. If you don't have one, go ahead and take a minute and fish it out. We'll do, I'm doing great on time. Does everybody have all of this? I've been doing so well on these that we pick a tricky one. Alright, so given the reaction below, where all of the concentrations of the aqueous compound. That's implicit, but I'll write it specifically. Why can that not refer to my solids or liquids? They're consumed to be 1 all the time. So, given the reaction where all the concentrations of the aqueous components are 2.5 times 10 to the negative second, I want to find these 4 things: Q, N, E0, and E. Preference on which one we start with. Q? Okay. This is the first one? Sure. Q. Alright, what is Q a measure of? What over what? Product or reactant? I'm going to fill in everything. I'm going to figure out what we don't actually need to have in here. Alright, so that's all the facts over all the reactants. Why do I have the OH squared? So you have two of them, right? Remember from last test. Still need to know that. Right, so if I have two of them, you have to square them. Good. What things in this fraction can I go ahead and cancel out? Let's look at the numerator. On the numerator, which of those things does not belong? The zinc or the hydrogen gas? Okay, why? It's a gas, right? Alright, on the bottom, there's two things that don't belong. What do not belong in the bottom? Okay, the zinc doesn't belong to the solid. What else? The water, right? Pure liquid doesn't belong. That was just more review than anything else. Alright, so this is an aqueous compound, so it must have that concentration. So that over that. Alright, so I have a Q equals to 40. Where are we at in comparison to 1? Greater than 1. Good. So what do we expect E to be compared to E standard state? Less than. So we're going to calculate and prove that's correct. Alright. If I want to go ahead and figure out, right, so we did 1, 2. If I want to figure out the number of moles of electrons transferred, what do I need to do? I need to do 2 half reactions. Awesome. Alright, preference on which one we tackle first, the zinc or the hydrogen? Wait, let's go with the tricky one. Alright, we'll do tricky first. Cool. What do I also need to include? Because, right, these are the obvious ones, right? I got zincs and zincs. What is included in this top part of the reaction that I probably need to include in this bottom part to make it mass balanced? So I put in the zinc, I get out of zinc. What do I also get out? I got 4 OH minuses, right? Right, if I get out 4, I must have 4. So if that is the case, have I now mass balanced this half reaction? I put in a zinc and 4 hydroxides, I got a zinc and 4 hydroxides. Mass, yes, good. Mass, we're all set, we're good. We'll worry about these guys up here in a minute. The fact there's only 2 up here, we'll come back to that. Alright, but looking at this mass-wise, we look good. Alright, next question. Who is changing oxidation state? The zinc, the oxygen, or the hydrogen? The zinc. Why is it not the oxygen? Because it's never the oxygen. Never, ever, ever the oxygen on these basic problems. Okay? So, if it's going to be the zinc, what is the oxidation state of my zinc solid? 0. Stop. Okay? What happens when I have this O and this H stuck together in a parentheses? What kind of charge does OH have together? Negative, right? Always -1. You could think about it like oxygen is -2 and H is usually +1. I think it's easier just to know that OH is -1. If I have 4 of them, but the overall thing is -2, well, it must be the zinc by itself. +2. So if I'm going 0 to +2, is that an oxidation or reduction? Oxidation. Where do I put the electrons? As reactants or products? Products, and how many? Where does the oxidation occur? The anode, the cathode, or the bridge? Anode, never the bridge. That was just a tricky question. Never ever the bridge. Alright. Questions on the first half? do the other half. Alright, I have two waters making a hydrogen gas, right, based on what I have up here. What is missing from this half reaction? What element am I not accounting for yet? Oxygen. If I have OH minuses left over, is this an acidic or a basic balance? It's a basic balance, right? So what should I use to finish balancing this? H pluses or OH minuses? OH minuses. So if I do that, right, over here I have 4 H's, I don't like calling them that, and 2 O's. Over here I've used up 2 of my H's. What do I have left? Alright, so then let's talk about who is changing oxidation state. The H or the O? H. What's the oxidation state of this hydrogen gas over here? 0. Over here, what are each of the H's worth? +1, right? So I have 2 plus 1 going to 0. So how many electrons do I need all together to get 2 plus 1 to go down to 0? Alright, looking at the hydrogen, is this an oxidation or reduction? Where does it occur at? Okay. Alright, we're now ready to figure out, I mean, we could do 2 things at once. What must n be equal to in this case? 2, right? So I put in 2 and get out 2. Alright, so then I want to figure out E0. E0 is equal to what minus what? Cathode minus anode. Where would I find those values if I were not given to you? On the handy dandy chart, so I'll go ahead and give them to you. Let's see. Alright, so it must be let me try to read this off the table right. Okay. Make sure I did my math right. Is that right? Oh, I see what happened. That makes more sense. It should be negative 1.2. There we go. Yep, I just corrected it. That should be a negative right there. Why did I know that a negative E0 was kind of funky? What did that tell me about the spontaneity of it? Not spontaneous. It would no longer be a voltaic cell. Because this is a voltaic cell question. If you get a negative E0, something's probably funky with your table reading. Or you dropped a minus sign someplace. Like I did. Dropped a minus sign. Alright. Now we're ready for the final concluding thought, right? I want to find E. Alright, so we just found E0. Alright, make one sense, these nearly biggie. Alright, R is the gas constant, right? It didn't tell us what temperature we're at. What is a really excellent guess as to what temperature we're probably at? Alright, and we found earlier was 2. And then Faraday's constant, 1.4. I forget this unit. There we go. That's joules, moles, Kelvin. Alright, 8.314. Alright, is this E less than the standard state E0? Yes. And our Q is greater than 1. So which direction is this reaction going to want to go? If the products are high, compare the reactants. Alright, Q is greater than 1, E is less than E0, which means I don't need very much voltage. Like, it's going to produce less voltage than expected, because it's going to want to come back towards reactants. Right. If I was at 1 molar, I would make 0.4 volts. But I'm not at 1 molar. I'm at 0.0025 molar. Right, so the voltage I get out of this is less than what I could get out of it. Make sense? Maybe. Okay, good. Yeah. So if you're at 1 molar, you would expect to get this much voltage. But you're not at 1 molar, so you only get that much voltage. You get less voltage than you could potentially get. How about we do another one? Okay. And then we'll get to electrolytic cells. Let's see here. Let's do... Alright, so given this reaction, you have lead solid and manganate makes a lead ion and a manganese oxide. It's in acid. I want to find number of moles electrons transferred, Standard state, Q, and E. Looking at this equation, what do we need to do first? Is it mass balanced? Alright, the leads look good, right? And the manganeses look okay. What's wrong? Oxygen. Are we balanced charge-wise? No, right? Because I have -1 over here and +2 over there. So what do you need to do before you can even solve the problem? Half reaction in acid. I'm trying to be helpful. All right, which half do you want to do first? Lead or the MnO4? Lead. Okay. If I did not tell you an acid, it would be really hard to solve, because you could choose acid or base. And if you chose base, it would take you forever to solve it. So acid's always easier to solve, because you just put in H pluses. It's just all balanced out. I'll probably only have acids on the exam in terms of balancing it. Like the previous problem was technically in base, but you didn't have to balance it, like it was already mass and balanced charge. Alright, so let's look at lead. Alright, what's the oxidation state of my lead to get started? 0. I'm going 0 to +2. Is that an oxidation or reduction? Okay. How many electrons do I need then as a product? Okay. Alright, let's tackle the other one then. Alright, who is most likely going to be changing oxidation state? The Mn or the O? The Mn, alright. So what should be the charge, the oxidation state of the Mn in this case? +7. Okay. Right, because oxygen is always -2. I have 4 -2, so that's -8. So I have a +7 to make the whole thing -1. So then what's the oxidation state of my manganese on this side? Alright, so I've gone 7 to 4, so an oxidation or reduction. Reduction. So if I've gone 7 to 4, how many electrons do I need as a reactant? Alright. What else do I need to balance out on this guy? Those pesky oxygens. Alright, so I have 4 over here and 2 over here. What is a good thing to add? 2 waters. Alright, so now I have 4 oxygens, 4 oxygens. Now what? That's 2. Yeah, 2 density. Good. Can I add them back together right this second? No, I would have leftover electrons. Bad news bears. So, what should I do to the lead reaction? Multiply by 3. What do I do to this one? Multiply by 2. Alright, now, question first one. So I had 4 oxygens and only 2 over here. So I add 2 waters. Now all the oxygens are balanced, but by adding 2 waters, I now have 4 H's. Right. There's 2 in 1 water, not 2 waters. Oh, and this guy? Sure, oxygen's always -2, and I have 2 of them. So this side is -4. And then since it's a solid, its oxidation state 0. Yeah. Alright, so now we're looking good, right? We're balanced. So we're now ready to actually start solving. How many electrons were transferred? 10 equals 6. Alright, Q is products of reactants. What products do I need to put in here? There's 3 options. Do all 3 go in? No. Just the lead, right? And so I didn't rewrite it, but the lead concentration's up here. That's this guy. What do I need to do to the lead? I need to cube it. Alright, so then what goes on the bottom of these 3 options? Yeah, I'm in a Yeah. If I want to be real crazy, I'll tell you the pH. And then you have to include the protons. But I probably won't be that crazy. Yeah. You wouldn't have the correct exponent. Right. Yeah. So you certainly could, but your answer would be wrong. So, so I always double check, right? Looking up here, I was like, oh, well, it's not mass and charge balance. So I don't want to do Q yet because I don't know what the exponent should be. Oh, it was already mass and charge balance. Why did you do that? Because you need to know how many electrons were transferred. Which you could have done by eye if you saw the whole thing with mass balance and charge balance. You can maybe work it out. But let's see, what was that? So how are we compared to Q? Bigger than 1, less than 1? Less than 1. So what would we expect the voltage to be that we get at non-standard state? Last one was less, this one should be more, right? Yep. Alright, so if that is the case, alright, let's figure out B0. Alright, and you would look these up on the table. Cathode, which is this manganese one, 1.68. The lead one is that. We'll plug those in. Alright, so if everyone was at 1 molar, I would expect to receive a voltage of 1.81. I'm obviously not at 1 molar, so I should expect not this voltage, and because my Q is tiny, I should expect much less voltage. Okay. I'll drop a negative sign. I'm kidding. There should be more. Where's the... No. No. Alright, let me try this. .87 times 10 to the 4th? No. Alright. I made this question up off the top of my head just before class started, so obviously I didn't try it out. Natural 4.4, 7. I don't think that seems like a ridiculous number, but you never know, right? Oh, I know I did. That's us. Yeah. I forgot the 10 times 10 to the 4th, which makes sense. Question, Chris. Or I'll give you the table. Yeah, you would have it at your fingertips in some kind of way. You wouldn't have to know those. Either I'm going to put it in the problem, or I'll have it as a table. I haven't decided which one's more efficient. It does not. Correct. Correct. Ever. Ever, ever. That's super exciting, right? Alright, so what I'm going to do, so I have enough time to give back everybody's stuff, is I have your quizzes to give back to you. So the last 2 slides of this chapter we'll do after your exam. So they only take about 2 seconds to do. Electric catalytics, whatever. So we'll review on Friday, exam on Monday, and then on Wednesday we'll do the last 2 slides of this chapter, and then nuclear chemistry. Which, spoilers, I'm in favor of. Very exciting. Okay.